talking about chapter 6 last week. We are here November 1st, chapter 6. We started chapter 6 last week. That was about plane stress and plane strain problems. Specifically, we talked about triangular elements, and we looked at the stress and strain formulas for plane stress and plane strain problems. So today, we are going to finish chapter 6, plane stress and plane strain problems. We are going to complete our discussion on triangular elements and look at a new type of element, which is rectangular elements today, at the end of our discussion today. And then next week, we move on to chapter 7, talk about practical considerations in modeling, and which is chapter 7, and also heat transfer problems. Those interested in heat transfer, that is the time to look at heat transfer problems. And then the week after, we will have a quiz also coming up later. So let's go back to our discussion. We didn't finish this plane stress and plane strain discussion that we had. We didn't complete. We were starting the variational method of finding the element stiffness matrix. So a quick review. This is a plane stress problem. We said that these are thin structures and these are two-dimensional elements we are going to discuss. So plane stress is this one, usually thin structures. Stresses are in one plane. And we talked about D matrix, material matrix. For plane stress problems, it is like this. For plane strain problems, we said these are usually long structures. We just take one slice of this and we model this as a plane strain problem. So strains are in one plane. Everything is in XY plane, nothing in the Z direction for strain. And material matrix or D matrix, it is given by this for plane strain problems. This is a triangular element. We looked at this one. We said it has 3 nodes. And this is node I, node J, node M. We said we label it counterclockwise. And each node has a displacement in the X direction and in the Y direction. UI, VI, UJ, VJ, and UM, VM. So these are the displacements at nodes. And these are the coordinates of these nodes, X, M, Y, M, XJ, XI, YI, and XJ, YJ. So this is our triangular element. We looked at the stress. We looked at these parameters, alphas, betas, and gammas. These are parameters in terms of coordinates of these nodes. And we found we talked about shape functions, and we found this B matrix strain is equal to this B matrix times displacements, nodal displacements. This B matrix, everything comes out to be constant. As you see, these are betas, these are gammas, these are nodal coordinates. So everything comes out to be constants. They are not functions of X and Y, in other words. So we looked at strain, it is BD, strain, and stress, which consists of sigma X, sigma Y, tau X, Y, it is DBD. This is material matrix, and BD. BD is this epsilon. So stress is material matrix times epsilon. Also, we looked at one example problem. I think we finished our discussion here. So what we are going to do, we didn't discuss this, I think, the principle of minimum potential energy. We were at the beginning. Am I right? Anyone remembers?
This is where we left off.
Yes. So we are here. Let's look at this minimum potential energy formulation, very important formulas we derived based on this, and then look at. Our goal is basically to find the element stiffness matrix, but we find it by minimum potential energy formulation. We start with this one, very similar to what we did for a bar when it was subjected to generalized loading. We said that total potential energy is U plus omega B plus omega P plus omega S. U is strain energy. It is given by this 1/2 epsilon transpose sigma dV integrate over volume. This is strain energy. Potential energy due to body forces is given by this C transpose X dV. X is body forces, force per unit volume, like density. If you want to include, for example, weight of a structure. So this is where it comes into picture, this X here, these body forces, potential energy due to body forces, potential energy due to concentrated nodal forces, omega P. So this is just omega is displacement vector times concentrated forces at nodes. And negative of work, force times displacement is work. Negative of work is potential energy. And finally, this one, omega S, this is negative C transpose TS. This is displacement. Displacement equations go here. This is traction, surface per unit area times ds integrated over the surface. So we put everything in this total potential energy formulation, manipulate a little bit, minimize this, and we derive important formulas from here. This one, again, similar to what we did before. This piece, it is epsilon transpose times sigma. This piece, it is sigma. So this gives you strain energy. Epsilon is BD. So epsilon transpose is D transpose B transpose. This is sigma DBD. This is potential energy due to body forces. You see, look at this one, this body forces. Displacement is always ND. And in this class, question for you, N represents what? Anyone?
Shape function.
Very good. N represents shape function. Very good. ND, so this is displacement transpose times body forces. This is force per unit volume times volume. This is dV, is force. This is displacement. Negative of displacement is potential energy. This is due to body forces. This is due to nodal concentrated forces. This is the same as this one, but here this is traction, surface forces. Integrate over surface here is ds. And then here, this is D transpose, D transpose, D transpose. These are displacements. Take them out of this integral sign. They are not functions of X or Y. So these are just nodal displacements. Take them out. It is this one, D transpose is out. D transpose came out of this. This is already dt out. This is dt, we brought it out. And then, so this total potential energy, we can write it like this. Factor this D transpose out. So it would be from here, it would be this one times D minus, there is D transpose, D transpose, D transpose, factor this out, minus F, where this F is this remaining term. This term, it is here in transpose X dV. This term, it is here, and this term, it is here. This is F. This is the definition for F when we factor this out. This is F. This piece, as you see, there is body force here. This piece, these are nodal concentrated forces at nodes. And this is traction, surface forces. This must be minimum, principle of minimum potential energy, which states that when a structure is in equilibrium, its potential energy is minimum. So this must be minimum. Derivative of this with respect to displacement. Derivative of this with respect to displacement, put it equal to 0. From here, we get what? We get this integral of B transpose dB, minus D is equal to F, or minus F. So this will be out, it is negative F. This piece, that's what we always like to see. This times D is equal to F. That's what in finite element we always want to see. This something is called K. It is our element stiffness matrix. That's what we want. This something multiplied by D is equal to F. This is the element stiffness matrix. Integral of B transpose dB. It's a very important formula. We apply it to different problems in future for different problems, different applications. Actually, this formula that you see I have highlighted is very important. We apply it, even problems in heat transfer, they end up closely like this one. This one is our element stiffness matrix. Now, for triangular elements, for constant, they have constant thickness. For plane stress problems, these are constant thickness. So this dV would be just thickness times dx dy. So our element stiffness matrix should be thickness times the same thing, but times dx dy. But for constant strain triangular elements, furthermore, this B matrix, this B here, you see, this was this. I have to go there back here. This was the B matrix. This was B. These are just nodal coordinates. So this everything is constant. They are not functions of x and y. So it means that this integral, in this integral that you see, this is B matrix, and this is material properties, this is material matrix here. They are not functions of x and y. So everything comes out. Dx dy becomes area B transpose dB. This is the element stiffness matrix K. Very important formula. That's what we wanted to find. K is TA B transpose dB. This is the B matrix, material matrix, and this is B. This is the element stiffness matrix. And the global formula, remember, KD is equal to F capital K. This is global. For all of the elements, we put them together. This is the global, and this is the general formula. Epsilon is BD, and sigma is DBD. DBD is stress. So in the equation that, in the see equation 643 of the textbook for explicit equation for K. Now, let's go back to our K. K is equal to this TAB transpose DB. If we multiply them, I showed you B a couple of times, and the material matrix B. If we multiply them, the explicit form for K is this. This is explicit form for K for plane strain problems, because you see here it depends on what type of material matrix we want to use for D. Is it for plane stress or is it for plane strain? So depending on which one we use, we get a different element stiffness matrix. It is given by this. It is a 6 by 6 matrix. It is symmetric. So what you see is almost half of this actually. This is thickness of the element, modulus of elasticity, area of the element, Poisson's ratio, and these are betas betas, 1 minus 2 nu, betas, gammas, betas, and everything else very similar. All right, this is for plane strain case. Now, if it is plane stress, make some substitutions very similar to this one. For plane stress problems, just replace 1 minus nu by 1. Whenever you see 1 minus nu here, you have 1 minus nu, for example, here you see. Replace it by 1. Replace 1 minus 2 nu divided by 2 by this. You see this 1 minus 2 nu divided by 2. Replace it with this for plane stress cases. And 1 plus nu, 1 minus 2 nu outside the bracket, but 1 minus 2 nu is squared. So if we make this substitution, then this would be the explicit form for plane stress case. But this one is already for plane strain problems. Computers don't like this one, actually. Computers don't like this explicit form of writing this. They prefer actually to do this multiplication. It is much faster for them when we find B matrix, D matrix, and do this multiplication. It's faster than just going and term by term, doing this term and going back and forth, finding them and plugging them. It's more time consuming than the direct multiplications. All right, that was our discussion about finding the element stiffness matrix. That was our main goal using minimum potential energy formulation. Any questions about this before moving on to remember here? So 2 items before I leave this document. This is element stiffness matrix, TAB transpose DB, and our F, this F is given by this. That's what we want to use it right now. I want to see what happens to this now. It consists of body forces, surface traction or surface forces, and also concentrated Nobel forces. Let's look at this one, each one of this individually, body forces, and let's look at surface traction. Let's go back to modules. All right, this is what we are going to finish this document and finish with chapter 6 of our textbook, plane stress and plane strain problems. Again, we ended up with that equation. Let's look at now what happens to the body forces. This was F I showed you. And we said that consists of body forces, this piece. Look at this X, this is body forces. Concentrated nodal forces and traction, surface forces. Let's look at one by one, body forces. Now, I want to look at this one, body forces here. This one. It is given by this, N transpose XdV. Now, this is a triangular element. It has 3 nodes. So this N would be Ni0, 0 Ni, Nj0, 0 Nj, and this is our N. X is our body forces. This is body forces in the X direction, body forces in the Y direction. Multiplying this, we get this. Now we have to integrate this. But remember, this is Ni, Xb, Ni, Yb. So these are shape functions, Ni. But these are the shape functions. Recall that Ni is 1 over 2a alpha I plus beta Ix plus gamma Iy. So and Nj similar to this and Nm. So these are shape functions. But they are functions of X and Y here. You see there is X and there is Y here. So we have to put it here and integrate over the volume. So it's a little bit not straightforward. It is easier if we put our coordinate system at the centroid of this element. So this is one of these triangular elements, node I. Jm. Put this coordinate system at the centroid of this element. If we do this, then these integrals of, like, for example, beta ix, you see this one, we have to integrate this here. So this one, beta ix here, then it would be 0. This is the definition for the centroid. So it makes this one 0. The same for this for example, gamma iy. We have gamma iy here. This would be 0. So this makes this integration much easier if we put this coordinate system at the centroid of the element. Then we can get rid of these terms, and integrating, this is the result of this integration, that our body forces, this FBIX, FBIY, this is at node I in the X direction, at node I in the Y direction. These are the body forces at nodes I, J, and M. It is given by this. This is body force per unit volume. Question for you, anyone, tell me, TA is what? Thickness times area. It gives, yes, say that again, louder.
Volume.
Very good. TA is volume. This is force per unit volume. 1/3 of the total force goes to each node. So if you want to include the weight of this structure, this is a triangular element, for example, you want to include the weight of the structure. Okay, well, 1/3 of the weight of this triangle goes to each node. If it is in the Y direction, let's say downward. So 1/3 goes to each node. This is very general. So 1/3 of the total force in the X direction goes to node between node I, J, and M, this XB. And if you want to include weight of the structure, for example, so 1/3 of the weight of that element goes to each of these nodes. So that's the meaning of this. All right, now any questions on this before looking at now surface forces? That was for body forces.
Is the file available? It says it's locked.
It is available. It is available. It's possible. Just go back and come back again. So it is available.
You can find it in the files section.
Oh, it just shows up as not been unlocked.
Let me check. Modules. This is what you see on the screen, what I show you, this one. This is November 1st to 5th. This is this document I'm showing you, and it checks that it is.
Yeah, it works for me.
It is unlocked. It is available to you.
Okay, I'll just ask someone else.
It is available. Maybe just exit from this, go to dashboard, then come back to this course, and then possibly needs to update something. Let's go back to this document, but it is published. All right. We finished with this one, body forces. Any questions about body forces before looking at, we discussed this one, body forces, before moving on to talk about surface forces. Any questions on this? All right, now let's look at surface forces. Surface forces is given by this interaction TSDS. This is this one. This is this formula. This is this. Interaction TSDS. This is the surface forces, but it needs, we have to see for what problem we want to apply this. It depends. We can do it we have to see on what surface we have the traction. So let's look at this example problem. As an example, let's look at this this triangle. Node 1, 2, 3, it has length L, this has length, this side is A. We are applying this traction on this side with P. We are pulling this. Let's see what happens to these body forces, these surface forces here in this case. Well, this is this one. Surface forces is given by this. Fs is n transpose, this is n. These are the shape functions. N1, 0, 0, N1, N2, 0, 0, N2. And this is our traction. Traction in the x direction, this one. And in the y direction, it is 0. Traction or surface traction, it is px and py. But in this case, we have just in the x direction. In the y, it is 0. So multiplying this by this, we get this one. Now we need to integrate N1P, N2P, and so on and so forth. So we need these items here. We need N1, N2, N3 here. So this N1, for example, here, it is given by this. Let's do it by hand here. Let's do one of these items by hand. Let me share this. So what I want to see what is N1, what is N2, what is N3 for this triangle here. So we can integrate and then find the surface forces. So we need this N1, N2, N3 for this case. To do this one, I will do one with you, and then you do the second one. Let me show you the camera. All right. Now, this was the triangle. We said this is node 1, node 2, node 3. This is our x-axis, this is our y-axis. And we said this side it is A, this side length L, and we are applying a traction P, this is pound per inch squared, let's say. To this, the question is, we need these N1, N2, N3. The question is, what is N1? What is N2? And what is N3? To answer this question, let's look at this one. N1, it is equal to 1 over 2A. It is what? Alpha 1 plus beta 1x plus gamma 1y. All right, I need these alpha 1, beta 1, and gamma 1. So alpha 1, what was the formula for this alpha 1? We need to look at the, since I'm showing the camera, let me look at the book. Let's look at the book for alphas and betas. This is here. In our textbook, alpha 1, alpha I is xjym minus yjxm. This is alpha, this is beta, and this is gamma. So let me write this one. alpha 1, it is xjym y3 minus y2 x3. This is this one. In this case, it is what here? This would be, what is x2 y3? x2 y3 is what? x2 y3, this would be 0 minus y2, y of node 2, this would be 0. So this is 0. This is alpha 1. Now beta 1, according to this one, it is our textbook, it says yj minus ym. It is y2 minus y3. What is y2 minus y3? Anyone? y2, it is 0 minus what is y3? Y of node 3 is what? 0. So this is also 0. This is alpha beta 1, gamma 1. Gamma 1, it is x3 minus x2. Oh, you can't see, you're not seeing what I. So what is this? X3 minus x2, x3 minus x2, it is a. Therefore, what? Therefore now, therefore our n1 is 1 over 2a, alpha 1, which we got 0, beta 1, we got 0, gamma 1, we got a plus ay. That's it. It is equal to ay divided by 2a. We can even simplify this further. It is ay 2a, twice this area, this 2a. 2a is twice this area, which is a times l. So this would be a times l, which is actually y over l. This a cancels with this. All right, that is the all right, agree with me. This is N1, which is the, we need to use it for, to do this one. Let me go back to, yeah, here, remember, this is the, this is what we needed. So we needed N1, so that was N1. We got this one, AY over 2A. I showed you this one. N2 and N3, we can find it similarly. I want you to find N2 for me. You have 2 minutes, find N2 for me. All right, 2 minutes. Tell me, what do you get for N2? 2 minutes. I'm also doing it here. All right, anyone got the answer for N2? Are you still working on this, or anyone got the answer? Anyone? The question was to find N2. This is what I did also here. N2 is 1 over 2a alpha 2 plus beta 2x plus gamma 2y. Alpha 2 is given by this. These are alpha, betas, and gammas. These are equations that we looked at before in our textbook. You can see that this is y1 x3 minus x1 y3. Just these are coordinates of these nodes y1. This is the figure here. Y1 is L. Y1 x3, y1 x3, x3, x of this node is A. So this is simply AL minus x1, which is 0. So this gives to A, results to AL. Beta 2 is y3 minus y1. Y3 is 0. We get negative L, and gamma 2 is x1 minus x3, which is 0. So with this one, plug them back into the equation for N2. N2 is 1 over 2a. This is our alpha 2, which was AL. This was alpha 2 plus beta 2x. This is actually beta 2 over beta 2. We found negative L. This is beta 2x. And gamma 2, it is, this is gamma 2. Plug them here, we get this one, L over 2a, a minus x, but for on this side, our x is L, our x is a. This x is a, so it makes 0. So N2 is 0. N2 is 0, and anyone got this one or not? Anyone got N2 0? I saw that one note in the chat. You got it?
How do you?
What is it?
How do you know which term in alpha and beta are subtracted?
How do we know which alpha and beta are subtracted? Well, here, of course, this is coordinates of these nodes. You see, this is alpha. Alpha is given by this formula. But these are coordinates of these nodes. What is y1? Y1 is what here?
L.
Y1 is L. Yes, this coordinate of this node. This node has, you can write it here. This node 2 has coordinates of 0 and 0. Node 3 has coordinates of A and 0. And this node 1 has coordinates of A and L. So these are the coordinates of these nodes. Just put them here. These are coordinates of this one. So y1 is L, x3 is A. So this would be AL, but this one would be 0 because x1 is 0. X1 is A, but y3 is 0. This one is 0. So this results in AL. And
yeah, I solved it and I got negative AL.
Oh, you got negative AL here?
Yes. So did I just
No,
zero.
This is y1 x3. Write it properly. y1 x3. y1 it is A. y1 it is L, and x3 it is A. So this is AL. This is positive here. And this term it is 0, y3 is 0. So it makes AL minus 0, it is AL. All right, this is for alpha 2, this is for beta 2, and this is for gamma 2. And then we put them back into this equation for N2, and we get N2 0. So that is for N2. And we do similar to this one for N3. Let me go back to our document. Put them back here, we get similarly for N2 and N3, I showed you these items. And then if we put them, we get this, the result of this surface forces, it is at node 1 in the X direction, at node 1 in the Y direction, at the same at node 2, and at node 3. We get this one, PLT over 2 and PLT over 2. You see here, this force is force per unit area, but L times T, this is length of this times thickness of this. LT is area of this cross section times P is total force. Total force, P times LT is total force. Half goes to each node. So it means that when we have distributed force on this side, PLT over 2, which means half of the total force that we are applying on this side will go to each of these nodes. All right. Any questions on this before looking at an example problem from our textbook? Any questions on this? Okay, well then I want you to participate, and if you have questions, let me know, but I will review this example problem with you. These are of course a little lengthy, so we review this by hand. It's a little bit tedious. Modulus of elasticity and Poisson ratio are given. This is a plate 10 inches by 20 inches, 10 by 20, and thickness is 1000 psi. Load is applied here. The question is to find the nodal displacements and element stresses. We want to see the stress, just coarse meshing, just 2 elements. Node 1, 2, 3, 4, 4 nodes and 2 elements. So this node 1 and node 2, they are fixed in the X and Y directions. Now, these 2 nodes, you see here, total force is how much? 1000 psi is the total, is the stress times this cross-sectional area here. 10 times 1, it is 10. So that 1000 times 10, it is 10,000. Half goes to each of these 2 nodes. So 5,000 pounds goes to each node, 5,000 pounds to this node. And connectivity table, element 1 and 2, we have 2 elements. So node start always go counterclockwise. So this element 1 goes from node 1, 3, 2. So this is 1, 3, 2. And this one, it is 1, 4, 3. Now, how many nodes do we have in this problem? Anyone? How many nodes?
4.
4 nodes. And how many degree of freedom per node? How many degree of freedom per node?
2 degrees of freedom.
2 degree of freedom per node. Very good. So we have our global stiffness matrix should be 8 by 8. But then because of displacement and displacement at node 1 and at node 2, 2 equations from here and 2 equations from here, they will be removed. So basically, in the end, we end up with 2 equations, with 4 equations for unknowns, which would be displacements in the x and y direction for nodes 3 and 4. To do this, we have to find the element stiffness matrix first. So this is the plate, 10 inches by 20 inches. This is our discretization, 2 elements. And this is element 1. Element 1 goes from, this is node 1, 3, 2. We need to find this B matrix. This is the B matrix. This is betas and gammas. We need to find them. Excuse me. These are betas and these are gammas, similar to what we did now today, finding these items. So this is our B matrix for element 1. As you see, these are all constants. These are numbers. There are no x's or y's here. This is our material matrix, D matrix. Plug the numbers, B transpose D. B transpose D is this one. So remember, element stiffness matrix is B transpose DB. B transpose D is this one times another B is the B matrix. Multiplying, we find element stiffness matrix to be given by this. And degrees of freedom, these are the addresses U1, V1, U3, V3, U2, V2. Remember the counterclockwise labeling. Do the same thing for element 2. These are betas and gammas. This is the B matrix for element 2, the same. These are all, again, constants. Material matrix, B transpose D. So element stiffness matrix for element 2 is B transpose D times another B here. And we get this one. These are the degrees of freedom for node 1, 4, and for node 3. And we have to sort them. Remember, this would be for node 1, 2, 3, 4. So sorting them like this for element 1 and for element 2. Finally, our global stiffness matrix, this is this one, 8 by 8. U1, V1, U2, V2, U3, V3, U4, V4. This is 8 by 8. Now, our system of equations would be like this. We have to apply the boundary conditions. Displacements at nodes 1 and 2. Let me show you the figure. At nodes 1 and 2, displacements in the x and y are 0. And this load is 5,000 pounds in the x direction at nodes 3 and 4, nothing in the y direction. So applying the boundary conditions, as what we do usually, this is the displacement out, and these are the loads in the x. We end up with 4 equations for unknowns. Solving them, these are the displacements U3, V3, U4, V4. Node 3 and node 4 have these displacements. But this is not very good. Let me see why. Let me show you. These displacements are, let me go and show the camera. Look at these numbers. I'm going to write them and show you on this one. So what we did here, this was the plate here. And we said, let me see, did we? I want to show you. Element 1, we call this one node 1, node 2, node 3, node 4, and we our element 1, 1, 3, 2. So this is what, not this one. So just remove, forget about this. This is our element 1. This is our element 2. Now, when we apply a force to this one, how is it going to deform? Let me show the deformation with this red color. We should have a displacement. I'm exaggerating, of course. We should have a displacement like this here, is it? In real life, we should get something like this, is it? I'm showing the deformed shape with this red line.
Yeah, that makes sense.
It shrinks here because of what? In this longitudinally, we are stretching this, but laterally there is contraction here because of the effect of, we call it what?
Poisson's ratio?
Poisson's effect. All right, very good. So we should get a displacement like this, but the displacements that we got are not really very, this discussion is of course important. I want you to see the behavior of this triangular element. The displacements that we found are these are the displacements that we found. We found U U3, V3, U4, V4. What we found are these. We said 609.6. I'm writing what we got now. 4.2, 663.7, and 104.1. Everything times 10 to the power negative 6 inches. Okay, this is what we got. Look at, they are not very actually very impressive. Here you see the displacement here is positive 609 at node 3. This one at node 4, it stretched more. This is not, it should be the same as this one. These are displacement at node 3 and 4 in the x direction. They are not the same. And we have a displacement in the y direction, which is positive. And so this shows actually that this node moved upward and this node moved upward even more. So these are not very good. Actually, this is completely wrong. We cannot have displacement positive. And these two, numerically, they should be the same, but they are it should be negative and it should be positive. So the overall, the result is not very good. Well, because we can attribute to this that it's a very coarse meshing. We just selected 2 elements. So let's look at the stresses. Let's see what happens to stresses. Let me share the so these are the displacements. The exact solution is actually this one. It is PL over AE, which is 670. So this should be actually 670, like this. And this should be also, this one should be 670. This one is okay, but this one is not good. This should be negative and the same as this one. But so the result is not overall very good. Let's look at the stresses. Stresses are sigma is dVd. dVd, we derived this formula before, material matrix, B times D. If we do this, we get this one, dVd, stresses for, plug the numbers, stresses, we get this one, 1005, 301, 2.4. We should only get 1000 PSI, actually, the load that we are applying here. Look at this one. We are applying 1000 PSI here. So we should have a stress in the X direction of 1000 PSI and everything else, no stress in the Y direction or no shear stress. So here we see that we got some sigma X is 1005, which is okay, but sigma Y, we shouldn't have any sigma Y, and tau XY, we shouldn't have any shear stress. Do the same thing for element 2. If we do dBd, multiply them, we get this one. Again, this stress is lower a little bit, and this stress is negative, which is not very good. It should be 0. Then the author found principal stresses, which we don't need it here. So some conclusions from this, I have written it here. These are some defects of constant strain triangular elements. These defects are these 3 notes here. Let me review with you. First of all, this we need to use finer mesh. Our mesh was coarse, so if we didn't get very good results. One discussion is that one argument is that we should make the mesh finer so we get better results. This was coarse. Constant strain triangular elements are too stiff when used in bending. As what you see, this shear stress, this shear stress here, we should not have it. So if you have a shear stress here, it means that it is acting rigid. This structure is rigid, stiff, especially when it is subjected to bending. This type of element behaves a little bit rigid. It induces stiffness, which makes the results are not completely, sometimes not satisfactory to what we want. In bending, especially, these constant strain triangular elements produce this false shear that I showed you, and it adds stiffness. It makes the structure behave stiff. This behavior is called shear locking or parasitic shear. This shear shouldn't be there. And this is called sometimes shear locking, this term here. And also in plane strain problems, when Poisson's ratio is 0.5, remember we discussed this before, it causes some problems. Sometimes some programs cannot handle this because it would be divided by 0, which is a problem. So in those types of problems, we have to pay attention when Poisson's ratio is 0.5, so the program can handle this. Otherwise, the program can stall or cannot handle these situations. Materials such as rubber, elastomers, Poisson's ratio approaches actually 0.5. So we have to make sure that the program can handle in these cases where Poisson's ratio is close to 0.5, and especially for plane strain problems. For plane strain problems, we run into this difficulty. All right, any questions about this before moving on to talk about quadrilateral elements, or more specifically, rectangular elements? All right, no questions. Let's now look at a more advanced type of element. We looked at triangular elements. We looked at constant strain triangular elements. This is a quadrilateral element with 4 nodes, node 1, 2, 3, 4. And the dimensions of this length is 2b and 2h. This is our XY coordinate system. Each node has 2 displacements in the X direction and in the Y direction, U1, V1, U2, V2, and the same for others. This is a quadrilateral element, more specifically a rectangular element. Quadrilateral element is more general when these angles are not 90 degrees. So that's a general case of a quadrilateral element. But this is a rectangular element when these angles are 90 degrees. This is also sometimes called Q4 element, or sometimes called bilinear triangular element. Now we will see why it is called bilinear. Again, this is 2b by 2h, dimensions of this one. Our element stiffness matrix should be, each node has a displacement in the X direction and in the Y direction. So it is, there are 8 components here. And again, labeling is counterclockwise, always go like this. So this element called 1, 2, 3, 4, like this. So with this derivation is very similar to what we did for triangular elements. So I go a little bit faster because we did the same, very similar. You start with the displacement function. This is U. Displacement function. This is displacement in the X direction. And displacement V in the Y direction. A1, A2, A3, up to 8. There are 8 unknowns. These are 8 A's that we need to find them. Applying boundary conditions, putting in this, finding A1 through A8, put them back into U and V. We find U and V to be given by these functions. This is U, this is V. And again, shape functions, we can write C as ND. And shape functions, there are 4 of them like this, N1, N2, N3, N4. These are the shape functions for this rectangular element. Again, they have the property N1 is 1 at its own node. Can somebody verify this? Is it true that N1, if you evaluate this at node 1, evaluate this 1 minute, is N1 equal to 1 at node 1? I want 3 people to tell me whether it is yes or no. Tell me if you evaluate this at node 1. We get 1 or not? If you want to see the dimension, this is this one. We are evaluating this at node 1, let's say. This is N1.
Yes, you do.
Yes.
All right, I heard 2 people. Anyone else?
Yeah, I agree as well.
Yeah, because for X, you did what? X is negative B and Y is negative H. because you see the coordinates of this node 1, its x is negative b, and its y is negative h. So if you put these coordinates here, you get 4bh divided by 4bh, so you get 1, so n1 is 1. And similarly to the others, we said that strain is in these plane stress, plane strain problems, it is given by epsilon x, epsilon y, gamma x, y. They are related to these displacement functions. Derivative of u with respect to x gives epsilon x. So we have u and v. Finding these derivatives, we find epsilon is bd, where b is given now by this matrix. That is, so this is strain. Once we have a strain, then we can find stress. But with epsilon given by this, there is a major difference between this one and constant strain triangular elements. Look at this one, tell me what is the difference? What's the major difference here? If you remember the B matrix for triangular elements, compare it to this one. There is a major difference here. What is that? The main difference is that there are x's and y's here. There are x's and y's here that we didn't have. The major difference is this x and y's. We didn't have these x's and y's before. Because when we want to integrate this and find the element stiffness matrix, then we have problems here. For constant strain triangular elements, there were no x's and y's here, so we could just easily, everything was constant. They were constant, so, but here we have to integrate, which causes a serious problem. Remember, element stiffness matrix is given by this, B transpose dB, dx, dy. For constant strain triangular element, these B terms in the B matrix, this is the material matrix, these are all constants. For constant strain triangular elements, these terms were constant, therefore we could just easily bring them out, and so it was just area. But for this case, it is not this B matrix, there are x's and y's, and we need to integrate this term by term, which is a big problem. We need to do numerical integration term by term for this triangular, for this rectangular element. So computationally, it is much more demanding compared to that triangular element. So pay attention to this one. Later, I want you now to show this page to you, comparing the triangular elements and rectangular elements. Very important discussion. I want you to participate in this discussion, ask questions and participate. But very important comparison here. This one is a cantilever beam, 1 meter by some dimensions here, which possibly it is given here. Length of this is given, and length is 1 meter. This area moment of inertia is given, so this height is not specifically given here. What we have is this one, cantilever beam, 4,000 Newton force we are applying here. We want to compare rectangular elements like this and triangular elements. We want to see how this one behaves compared to this one, with different types of, different number of rows and different selections here. We are comparing them in this table, table 6.1. These are Q4, these are rectangular elements with 2 rows, 4 rows, 8 rows, and constant strength triangular elements with 2 rows, 4 rows, and 8 rows. Now, number of nodes here, 60 nodes, 200 nodes, 720 nodes, and the same for triangular elements with 2 rows. We have 60 nodes, 200 nodes, when we have 4 rows, and 720 nodes. Let's compare the deflection at the free end here. So this beam will deflect, will move downward. Let's find the deflection downward of this end here. If we do the exact solution, we get this one. This is the exact solution. 6.67, 2 times 10 to the power negative 4 meter. Now, rectangular element with 2 rows, we got 5.944. Very coarse, even just 2 rows. And with 60 nodes, we got this one. Compare it 5.9, 6.6, but it is very coarse. If we add, make it 4 rows, overall 200 nodes we get 6.509. Compare it to this one, very quickly it approaches the exact solution, 6.5, 6.67. And then if we make it 8 rows or 720 nodes we get 6.66. So very close, converging to the exact solution. But now look at triangular elements. With 60 nodes, 3.6 versus 6.6. It's not good. It's too much, almost half of this. And if we increase it to 4 rows or 200 nodes, we get 5.5. And if we increase it to 8 rows, 720 nodes, or this time number of elements, number of degree of freedom, it is shown 6.3. What do you think? Which one is behaving better, quadrilateral or triangular? Which one do you prefer?
Quadrilateral.
Quadrilateral overall is behaving better. Even with just 2 rows, we get this one and very quickly converges to this one versus 3.6, which is not very impressive. Look at the stress now. Stress, this is 0.05 meter from the wall here to avoid this stress concentration at the boundary. We have this one. This is the exact, we should get 19 megapascal. For Q quadrilateral element, we got 17. Even with just 2 rows, we got 17 versus 19, but then 18 and then 18.9. So very quickly it is converging to this. But look at triangular with 2 rows, it is 7, which is not good at all. And then with 4 rows, we got 13. Still, it is not good. And even with 8 rows, it is not even. So with this one, you see it converges much faster. All right. So as what you see here, the behavior of this quadrilateral element is better. The reason is because the stresses vary linearly over the element in the x direction and in the y direction. For constant strength triangular elements, stress is constant over the element. But for this one, it is bilinear, it is varying. So let me show you one more figure here. Let me draw this one. Let me go back to the camera and see what this was the problem from the I want to suppose analyze this problem. Suppose I want to select this one, node 1, 2, 3, 4. Node element 1, element 2. Tell me, which one? I want to do a stress analysis of this one. I selected 2 elements like this. Is it very bad, bad, okay, good, very good? What do you think?
Very bad.
Anybody else? Anyone?
Very bad.
Very bad. Why very bad? I agree with you. Very bad. Why? Well, because this is giving one stress over this element. For example, element 1, we get 1 sigma x. There is just 1 sigma x for this, but it's not correct. I mean, this stress is varying. Even these fibers are in tension. Then these fibers at the bottom are in compression. When we apply this, these stresses are positive, and they are varying linearly up to this neutral axis, neutral plane, and then these stresses vary linearly like this. So this sigma x should actually vary like this. And these stresses are actually, they are actually compressive, they are negative here. So just one stress sigma x, it is very bad. It is not modeling it properly. So at least we should have divide this into 2 rows. So this stress is positive, and when you apply a load, this stress is positive and this stress is negative. At least it makes better sense. But the more the number of rows you divide, the better it would be, especially when stress gradient here is high. Stress is changing rapidly here because of the presence of this wall. So wherever stress gradient is high, make sure that you select more number of triangular elements. But overall, we can achieve the same thing or better with less number of rectangular elements. All right, with this one, let's go back to our document. A couple of just notes here I have to complete this discussion. Advantages of rectangular elements over constant strain triangular element. It is easier to create the input, create the mesh, and simpler interpretation of output stresses. Stresses are easier to see because these sides are parallel with the sigma x and sigma y. But the disadvantage is that poorly approximate boundary conditions. In general, triangular elements are better for curved boundaries, for edges. When we have curved surfaces or so, they do better versus rectangular elements. All right, so these are the disadvantages and advantages of using rectangular elements. All right, so today, briefly reviewing, we discussed this one. We started with, of course, potential energy formulation. We found the element stiffness matrix. This was the force vector. And we looked at body forces and surface forces. Applied to these surface forces, we looked at this one that it divides it to half of the total force goes to each of these nodes, and this node doesn't get anything. This node 2 is not affected by this, as what we saw here. This for node 2 in the X and Y, we didn't get anything, but just node 1 and 3 in the X direction share the half of the total load that we are applying here. And then we looked at also the rectangular elements, and we saw that they behave in general better because of this, because stress, mainly because of this, where is the B matrix? The key is here, this B matrix, compare this one to the triangular elements, these X's and Y's make this stress as sigma X and sigma Y very linearly over the element versus the constant strain triangular elements with stress was constant. And this example problem was very helpful to compare the behavior of these two. All right, that was our discussion for today. Any questions about what we discussed today? All right, if no questions, for the lab, for the project on Wednesday, we do not meet. There is no need to come to Zoom. We do not meet. You are working individually on this project. If you get error or so, try to see where the source of error is. We did enough practice throughout the semester, so it is important that you practice and find the source of this. If you get error, pay attention that you need constraints. You need to have constraints and pay attention to the boundary conditions. But problems always require some type of constraints to be able to solve. All right, so we do not meet on Zoom for the project. You work on the project yourself, and we will meet for our class next Monday. All right, I stop here, everyone. Have a good rest of the day. I will see all of you on Monday for our class.